Now I've got to give you the bad news. You knew it was coming. Just when you feel good about a calculation, what do? We turn around and we throw a curveball. All right, what's the curveball here? Well, we've talked about two reasons to use a t-test, really. Of course, you can look at it as the same one if you really want to. We took a sample into the laboratory, we tested it multiple times, and we report a window. The true value is within this window. And we can report that to a client, or we can compare that to an accepted value if the lab has ordered a standard for me to test, just to make sure that everything is in line the way it's supposed to be. All right, well, here's another reason to use a t-test or a confidence limit. We typically call them just t-tests because we use the student t, which is in reference to the confidence limit, so we're really talking about the same thing. So in this example, another reason to use that t-table is to compare two things. What are we comparing? Well, we can measure a quantity, one sample only. One sample has been brought into the lab. We measure that sample using two different methods. Okay, so for instance, I take the sample, I analyze it on one machine. I then take that same sample and analyze it on a second machine that's completely different. Are the two instruments telling me the same thing? I know they're not going to be identical. They're two different instruments. They operate in a different manner. Maybe one's by hand, right? Maybe I've got to process one of them by hand the entire time. Maybe one's a little more automated on a piece of equipment. Who knows? But there's two different methods there. We know that the answers are going to be different. They are not going to be the same. How far apart are they? Is it acceptable, or are they telling me something different? That is the other reason, another reason, to use a student t-table. All right, so what does the equation look like? Brace yourselves. You ready? Bam! There's the equation. Woo, and it looks like a doozy, and it is a doozy. So this is the equation that I use. I'm even too lazy to write it out. When I want to compare two methods with each other. Now, even though it looks complicated, I want you to take your time and look at the variables, because you know what all of these variables are. X bars are averages. S's are standard deviations. N's are the number of samples. The only difference here are the subscripts. Subscript of 1, subscript of 2, subscript 1 and 2's, subscripts 1 and 2's. That is the only difference. And the reason that we're doing that is because in the equation, or in our example, what are we doing? We are comparing two methods. Whatever they are, we're comparing two methods here. So that means in this equation, we have to represent that. We have to make sure that we are including both methods. One of the methods will have an average, a standard deviation, a number of samples. The other method will have its own average, its own standard deviation, its own number of measurements. They don't have to be the same. We can analyze a sample 6 times on one method, 8 times on another, and compare the two. Who cares? We can do that. But that's why the 1's and 2's are there. 1 represents one set or one measurement, and the 2's represent the second set or the second measurement. So, way that we read this, this is the average of your first method. The x bar 2 is the average of your second method, whatever that might be. This is the absolute value. That's what these bars mean on the sides. So if you end up having a negative number here, you ignore that. You get rid of the negative number and you turn it positive. The N1s and the N2s, the number of measurements that you took with your first method. The number of measurements that you took with your second method. The same down at the bottom, divided by the number of measurements with your first and the number of measurements with your second. Notice that the square root of that entire calculation. And then the only other piece here is this thing called S pooled. Well, the reason they put S pooled here is because there's so much garbage that goes here in the denominator that they write it separately over to the side. So this section for S pooled has to be calculated. And S pooled, that's the piece down here at the bottom, is this equation. So this is your standard deviation of your first method, and you square that number, times the number of measurements in the first method minus 1. That is degrees of freedom right there. Plus standard deviation of your second method squared times its degrees of freedom. Number of measurements minus 1. Divided by number of measurements from your first plus the number of measurements from your second minus 2. Again, think degrees of freedom there, right? You got two methods. You would have normally subtracted one from there and one from there, so you're subtracting 2 in total. So once you clear this up for S pooled, whatever number is there, because you got to take the square root of that as well, whatever answer you get here, that's the answer that gets put into the denominator up here at the top. So these are two separate equations, really. Solve for your S pooled. That number goes into this spot right here in the denominator. And then you'll carry the calculation on through using the equation up here at the very top. All right, so let's look at an example problem. We'll work through it. We'll hold your hand. We'll make it through together. And you'll realize it's not that bad. So here's an example. A sample of gas was obtained in the laboratory. An average mass of the gas from method 1, whatever that method could be, who cares, it doesn't matter, was found to have an average of 2.31011 grams. And a standard deviation of that was 0.00014. They did that 7 times. 7 replicates. That was their average and standard deviation for that method. Then that same sample, that's the kicker, the same sample was analyzed again on a different method. We called that method 2. Who cares what that method is going to be? Doesn't matter. And it had an average of 2.29947 with a standard deviation of 0.00138. And we did that 8 times. So a person did an extra trial run. It doesn't matter. We can do that. That's legal. Are the two methods the same? And in parentheses it says use the 95%, right? We said if it doesn't really tell you, go to 95 every single time, but use the 95% here. All right, so if I take a look at the averages, 2.31 and the other one's 2.29. Those two numbers are really close together, right? This is the average mass, 2.31 and 2.299. Super, super close. The standard deviation here is 0.0014, and this one is 0.00138. So it looks like this method, I get tighter numbers. The numbers are closer together. This standard deviation's larger than this one. So this standard deviation means the numbers are a little spread, right? They're not as tight. They're not as close together. All my darts aren't in one spot with that method. But the question here is, are they the same? Yes or no? Can I use either method? Well, by first looking at these values, 2.31 and 2.299, that's super duper close. But again, how close is close? That's what the student T is going to tell me. That's what these confidence intervals tell me. Is it close enough? That's always the question that we ask. So in the next video, we will go through and I'll go step by step on plugging numbers into that horrible looking equation that you saw, and we will work through this together. And even though it looks nasty and trashy on a sheet of paper, I promise you, if you know where the numbers go, it cleans up very quickly. And that's what we'll do in the next video. We'll work the example out. Stay tuned.